First, I'm going to be discussing the transient response to a second order system. So remember, the transient response is the first few seconds of the response while the system is still stabilizing itself. So, first of all, I want to tell you that if you want if you want more details on the transient response to different inputs, because we can have different external force inputs. We can have like a step input, an impulse, which is like a kick. We can have a ramp. So these are the typical inputs. So external inputs. If you want to see a more formal discussion on what's the exact response to an input, so for a second order system, the transient response, I highly suggest you to check Mandel's book. I told you before, it's a great book. I love it. He's done a great job at this. Very nice analytical analysis on the transient response. Well, on everything on stability is just great. It's very well explained, step by step. You can pick it up even if you don't know about control theory, so I highly recommend this. So I'm just going to go really over the transient response. What's it going to be like? So for our rockets, the transient response is going to be it's going to have some things in common, okay? It's going to be really undamped. So I don't care about, what kind of inputs I have as an external moment. By the way, it's not always easy to model an external moment. For example, imagine that our rocket is flying vertically and suddenly it finds a lateral crosswind. Well, this isn't actually a step moment like Mandel defends in his book. It's something I discussed with him, which I think the model, I think it's not correct. Maybe the kind of response it has is similar, but if you have a crosswind, it certainly causes an angle of attack, but the rocket tends to stabilize it at alpha equals 0. So the rocket will tend to alpha equals 0. So Mandel, what it suggests is that a lateral crosswind, a sudden lateral crosswind, can be modeled like a step. So if this is the external moment applied on the rocket, it can be modeled like this. Like suddenly I have like a torque. This would be like giving the rocket a torque. But this is incorrect, because if it were to be like this, the response is going to be looking like this. This is alpha, this is time, and the rocket will never stabilize at certain alpha 0. It would stabilize at this would happen if a crosswind could be modeled as a step function, as a step torque. But it certainly can't, because having a crosswind won't mean that your rocket will stabilize flying at a certain angle of attack. It's not going to fly like this all the time. Of course it isn't. It's going to try to minimize the angle of attack and get it to 0. Still, for the analytical analysis, the transient response say the input isn't so important actually. I'd say because also apart from it's difficult to model, say, a crosswind or the different real perturbations that the rocket can have. It's not so easy. The good thing is that all these external inputs have things in common. So they're undamped, which means that it's going to oscillate. And then there's always some kind of form of an exponentially damped sinusoid, which means that alpha is something like this. Say just a constant, then an exponential that is this would be something like this. Well, not quite. This would cross. Let me draw it again. Well, you get the idea of what this function is going to be like. But let me do it. So e to the minus dt is going to be something like this. This tends to 0. And this is multiplied to a sinusoid. So sine at a certain angular velocity w plus phase angle. Okay. So what this is just multiplying this function with, typical sinusoid. So you get this, a damped sinusoid. So this dampening is obviously due to this damping exponential. And so yeah, we're always going to have this kind of, wiggly function. A damped sinusoid. That's what it is. And d is the inverse time constant, and d is equal to the damping ratio times the natural frequency. And the d, which is the inverse time constant, is going to tell us how fast this is dampening. So remember that if we have, for example, d equals so after, for example, twice the time constant would be 1 over d. This exponential is going to be, so this is 2 over d. This is going to be already 15% or 14% of the initial value. So imagine this is a. This is 14% of a. So after only twice the time constant, this perturbation has practically faded away, right? And then after 3 over d, this would be like 5% of a. So more or less, 2 over d is already this perturbation has faded away. So inverse time constant. We still have to see what the damping ratio and the natural frequency is for our rockets. So in terms of, we want to know, We want to know what this is like, but in variables we're familiar to. So we want to know what this is, but in function of, we've seen this variable, we've seen the diameter, we've seen the dynamic pressure, the aerodynamic center of the fins. We're gonna see that in a moment, but right now I'm just explaining like a general, just an overview without substituting our variables. This is just general for second order systems. The response, well, in this case, it's for undamped systems. And by the way, the separation between, the time between oscillations is pi over the angular frequency, and for this isn't too important, but still I'm just pointing it out. For very undamped systems, which is our case, the angular frequency is going to be practically the natural frequency of a system. So in the next video, I'm gonna discuss the steady response. So yeah, this is just an overview of the transient response. Remember, if you want more details, use the tech manual. I'm not gonna go into much detail on this. The most important things you should note that the inverse time constant is equal to the damping ratio times the natural frequency. This is the so the higher this is, the faster the rocket is going to damping out perturbation. So it's going to be faster in damping out perturbation. So we're going to want that high, so it's not going to oscillate forever, because think about every oscillation means that we're going to have an angle of attack. More angle of attack means more drag. So in general, this is the most important thing you should know about the transient response. Okay, and the rest, it's nice to know like the exact function, but I think it's more like for the love of art. So if you want to know the exact response, you should check Mandel. I'm not going to go through it because I don't think it's that important. It is more important the steady response. We're going to see why in a moment. And then what I'm going to do is finally when I explain to you the transient response and the steady response, we're going to see what these values are. We want to know what the natural frequency is, the damping ratio is, in function of the variables we already know about our rocket.